of our great friends at Cornelis. Please welcome to the stage, Matt Williams.
Hey! Well, hello everyone. Thank you for coming. And yeah, we're definitely very strong and proud partners of AMD. And really, my talk today is about how you supercharge EPYC CPUs with our advanced, world-leading scale-out networks. So Cornelis is an up-and-coming name. You may not have heard of us, but you've probably heard of Omni-Path, which was developed by Intel spun out about 5 years ago. And the nice thing about Omni-Path is it is designed for the needs of HPC and AI applications. So we're all about latency, we're all about message rate. We are HPC and AI experts. We have computational scientists, we have deep network technology. Everything we do from the hardware to the software stacks is all designed about maximizing HPC and AI application performance. I'm going to show some benchmarks later. You'll see it's not just a small advantage, it really is an unfair advantage versus some of the other technologies that are available in market. And the partnership we have at AMD continues to grow, continue to be very strong. And when you take a look at the combination of the power of AMD EPYC processors and the performance and scalability of a Cornelis network, you really do get leadership application performance. You get very, very powerful scalability. And the most important thing is choice. Right? There are vendors, there are ecosystems where choice is not allowed. What we provide our customers and AMD and our joint partners is that choice. An open ecosystem, a powerful network, and together delivering world-leading application performance for almost every HPC code and AI applications as well. So one thing we announced very recently is a best-in-class, you could call that a world record, for one of the commercial codes with Ansys Fluid, recently acquired by Synopsys. And this is 30% higher than performance on the same system versus InfiniBand. So if it's only 8 nodes and Fluent runs 30% faster, you can do 30% more modeling, get 30% more accuracy. So and even on an 8-node cluster, commercial codes, open codes, all run faster. This is actually twice the previous published benchmark on the same number of cores. So phenomenal performance with our friends at Ansys, and of course with AMD. So a bit of a roadmap. So we were very proud to launch the CN5000 at ISC in June in Germany. It is a 400 gigabit platform, both switch and NIC, and it is based on our Omni-Path architecture. And Omni-Path you can think of as synonymous with HPC performance. We have adaptive routing, we have advanced congestion and flow control. We have a lot of the base level features that are now being recognized by things like Ultra Ethernet as being critical to performance. We have link level retry, we have credit-based flow control, we have all those technologies already proven out at scale in production. So if you like those features, you'll love the product. We announced this week as well the CN6000, which is an 800 gig evolution of the CN5000, where we're adding hardware acceleration for RoCE and a full Ultra Ethernet compliance on the SuperNIC side. And our customers want choice. As technologies like Ultra Ethernet evolve and catch up to where we've been for a number of years, we're going to start to offer those technologies. Customers always want performance first. Now we start to offer protocol choices on the world's fastest NIC, the world's best switches. And the CN7000 2027 is a 1.6 terabit platform, 64 by 1.6 terabit switches, will be full hardware acceleration for Ultra Ethernet, for RoCE of course, as well as Omni-Path. So we'll be fully compliant, fully compatible third-party systems, and still deliver best-in-class performance for all HPC and AI applications. We also invent adding in-network computing with RISC-V processors, again, offering choice, offering compatibility, enhancing the open ecosystem with our partners. So we are a unique technology today, although the software stack is completely open. We invented libfabric, Ultra Ethernet adopted libfabric, we lead libfabric and Ultra Ethernet. So from a software perspective, these advanced technologies are very easy to deploy. Everything is upstream to the kernel, everything is open source. So we have a SuperNIC platform, which is a custom silicon that's designed primarily for latency and message rate performance. It doesn't have deep security features like Ethernet might have. It doesn't have all these things that aren't needed in the HPC and AI application space. It's all about performance. We also have a custom switch ASIC available in a couple of form factors. market-leading latency performance, market-leading congestion handling. It really is the best possible solution for HPC and AI applications. Then we have a unique form factor where we compress 36 switches down into 17 rack units and allow very high density HPC and AI deployments. If you take a look at some of these highlights of our performance, this is on EPYC processors, 9755s, on the same system versus NDR 400. So the same line rates, we get 2.5 times the message rate of NDR. We have 45% lower latency. And so when you take those things together, applications just run faster. And so some of our spec MPI benchmarks are showing a 2x performance increase, again, on only 8 nodes. So tremendous performance increases, very easy to adopt due to our huge support and adoption of all these open standards. So I'm going to go through a couple of reasons why we're so fast. And effectively, we built the hardware alongside the needs of MPI, SHMEM, other advanced applications, and of course AI applications as well. The first thing we do is recognize there's a difference between small and large messages. When you want to send small messages, the bottleneck isn't bandwidth, the bottleneck isn't the bus, the bottleneck is how quickly you can send a message out onto the wire. And what we do is we are about half the CPU cycles to send a message than anyone else. So for every write in your code gets dedicated hardware, and that code just talks to the hardware directly. A memory write, MMIO through PCI Express, and it just sends the message out. So very, very fast, optimize the small message performance. And but at a threshold you set every time you run a job, we can switch to a DMA capability. We have 16 DMA engines and a service in the kernel that manages them to optimize the requests from all the bulk data transfer going on in your ranks. It's all done automatically by our optimized loop fabric software, OPX. So again, you get best possible small message performance, best possible bandwidth ramp, all in a very easy to deploy, high performance solution.
Try to also implement multi-tenancy at the same time.
Yeah.
That they're solving this problem.
So the question was around multi-tenancy and our support for it. We support SRIOV for physical hardware isolation on the node. We're developing Kubernetes capabilities to do isolation there. We have a technology called vFabrics, which is an extension of PKeys that has QoS capability. You can dynamically add and remove tenants. So yes, the question is multi-tenancy, and we have the hardware and software to do that as well. So link level retry, why is this so important? Why has Alt3Ethernet adopted this? Well, the rationale is if you take a look at the top right, 10 to the negative 12 is, how often does a bit error occur in a link? That means, at 1 out of 10 to the 12 bits is error, but we're sending 400 billion bits per second. So you're getting a bit error every 2.5 seconds on every link in your network. And this is going to get worse and worse. As you're using things like PAM4, your bit density goes up, your signal rate goes up on the lines, you're going to see more and more bit errors. People apply FEC to try to correct the bit errors, but you get escapes. So you always have bit errors in networks. It's just a fact of life. In every other network, we get a bit error on a link, it corrupts the packets, and the next switch or the end host will recognize the corruption and discard it. So a packet loss event occurs every time there's a bit error. In every other network, what you have to do is request retransmission to the source. And so you have a delay while data is no longer being delivered. You have a delay of having to send a request back, and you have a delay of having to send the data again. And a lot of these are called back-end approaches to error correction, which means you retransmit good data as well. And because a lot of software stacks see packet loss as a congestion event, even though it's a bit error, the stack slows down. So a huge impact on performance every 2.5 seconds on every link in your network. What we do at Cornelis with Omni-Path is we recognize bit errors locally on the switch. We retransmit locally on the switch. The switch is holding on to data until we know it's successfully been delivered to the next hop. For retransmissions of hundreds of nanoseconds, applications never notice. We are the only truly lossless network. Even InfiniBand, in the presence of a bit error, loses packets. So that consistency of performance, you need to make sure you maintain it even under real-world conditions with all of these bit errors that are going on. And then buffer credits, familiar to people who know InfiniBand and private channel. For those looking at Ethernet, this is another technology being adopted by Ultra Ethernet. With Ethernet, switches just send data when they want, effectively, with base rate technologies. And so we have very large buffers to absorb bursts of data from a peer. And so you have, whenever that buffer fills up, you add latency to the system. So the tail latency in a sort of a lossy system is always very high because these buffers are absorbing the bursts. And you still get bulk packets. What we do in our system is we negotiate the sizes of the buffers, and link partners never send more than will fit in the current buffer. So you protect it, and you can have very thin buffers, you can maintain your tail latency performance. And these technologies, I said, being adopted by Ultra Ethernet. We offer it today in an open ecosystem, in a system that's been proven over years at large-scale production. Some micro benchmarks. On the left-hand side, we have latency. This is a A/B test, apples to apples, with same systems, of both AMD EPYC 9755. Same single switch. On the left-hand side is one process per node, just talking back and forth in a ping pong. And you can see versus NDR at 8 bytes, which is a key message size, we're 32% lower latency. The scale for the HPC message sizes up to 16K, or up to 45% lower latency. Look on the right-hand side, the other key metric for HPC applications is message rate. Code is sensitive to latency or message rate, you know we're going to do well. If you take a look at our bandwidth ramp up to half bandwidth, we dominate there as well. So pretty much every code will run faster on an Omni-Path network. Just to show some data points, this is some spec MPI running on the EPYC 9755 8-node cluster. So again, only 8 nodes, only a single switch. And we're able to drive some of those spec MPI codes up to twice the performance. So the code completes in half the time because you've removed the bottleneck. Where HPC and AI, the bottleneck is the network. So it's very, very important to address that. Omni-Path is the best way to do it by far. Again, easy to adopt due to our open software stack. Physics and life science is also 2x, climate 46% higher. As we continue to tune these applications, we're seeing improvements almost on a daily basis, different codes as we take a look at them.
Is this all handpicked, or do you have any cases that actually are Cornelis?
The question was, are these handpicked, or are the ones where there's below NDR? So there are cases today where some of the spec MPI benchmarks were maybe 2-3% behind. We consider that a bug. It's not a software bug, it's not a hardware bug, we haven't had the time to tune that application. So this is just a harness that we do continually on the system, and it's out-of-the-box performance metrics. None of these have been tuned for us. We just follow NDR guidance as well, though. So yes, there's upside to all these codes. And the announcement this week is our CN6800-GB SuperNIC. This is where we really double the CN5000 pipeline. You can think of this as a family of products, the 400 gig and 800 gig, using the same silicon constructs with more resources for even higher density CPU cores. We'll be delivering 1,600, 1.6 billion messages per second in this platform. Again, by far higher than any other technology available, while maintaining that sub-microsecond latency performance you saw in the micro benchmarking slides. So again, industry-leading performance for 800 gigabits per second. We have two 400 gig ports. Similar to other technologies, we can switch between modes. You can run in full Omni-Path for the best possible performance. But because we're about choice and openness, we also allow customers to switch to a hardware-accelerated RoCE capability on either of the ports or both, as well as supporting full Ultra Ethernet compliance for Ultra Ethernet transport. So summarize, we have the best performing network, and it makes your codes run the fastest. Choosing Omni-Path will always deliver you, best possible results, and we've been proven. All these advanced technologies are being adopted by other sort of standards, have been proven out by us over years. So we are the experts in these technologies, and as we continue to innovate as a smaller company, we'll continue to stay ahead of the game with full compliance, but a best-in-class application performance. That, of course, means you're maximizing the efficiency of your cluster. Your CPUs are doing more work, your GPUs are doing more work, or idle less of the time waiting for data to run. So that's it. Any other questions before we raffle it off?
Our booth is right there.
Oh, and sorry, I was reminded, our booth is right there. So if you want to see a switch, a NIC, and a director class, which is very cool engineering, come by and visit us at the booth.